Dundigal. My name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is Computer Architecture. Today I am discussing about floating point arithmetic operations. So, basic considerations of floating point arithmetic operations are: a number of computer registers consist of two ports, mantissa m and exponent e. The two parts represent a number obtained from multiplying m times a radix r raised to the value of e, thus m into r power e. The mantissa may be a fraction or an integer. The location of the radix point and the value of the radix r are assumed and are not included in the registers. For example, we are taking one example, a fraction representation and a radix is 10. The decimal number is 537.25 and the representing the register value is m equal to 53725 and e equal to 3. And the mantissa in representing in the present of floating point number is 0.53725 into 10 into 10 power 3. So, before going to this floating point arithmetic operation, so what are the floating point numbers are there? Suppose we have to take, suppose I equal to 1, here I equal to 10 like this. These are the integers are there. When we are going for the floating, 0.134 or 2.134 into 10 power 4 like this. So it is one example of floating point. So here we have mantissa is there and exponent is also there. Here only the mantissa is there. Here we have exponent also there. So we have to consider mantissa and exponent for the floating point arithmetic operation. Suppose I am taking a two parts of representing number obtained by multiplying m times a radix r and the value is e. M into r power e. That means here one taking one example 537.25. So we are calling as it is a mantissa and we have to convert to the exponent. So here 0.53725 into 10 cube. So it is a mantissa and we are taking as it is a exponent value. So we have to balance the mantissa according to the exponent value, and the mantissa may be a fraction or an integer. Maybe here 537.25, maybe I will take 537 into some 10 power like this. So if I am taking like this, it is maybe an integer. I will take the not only mantissa integer, we have to take the fraction value or floating point also. So the location of the radix point and the value of the radix r are assumed and are not included to the registers. So here we are taking one example, the radix 10, the decimal number is 537.25. It is a decimal value. We are representing in a form of register with m equal to 53725. So I have to define these values are in the form of 53725. So here and e equal to 3 and is integrating representing the floating point number is here. What is exponent value? 3 is there, but my value is 53725. So we have to convert to the 0.53725 into 10 cube. Floating point addition and subtraction. During addition or subtraction, the two floating point operands are in AC and BR, accumulator and basic register BR. The sum or difference is formed in the AC accumulator. The algorithm can be divided into 4 consecutive parts. First one, check for zeros, align the mantissa, add or subtract the mantissa, normalize the result. So these are the 3 conditions or 3 algorithms can be divided into consecutive parts. First, check for zeros. Is there any zeros are there in the input, and check the alignment of the mantissa and or subtract the mantissa, normalize the result. So these are the conditions for floating point addition and subtraction. A floating point number that is 0 cannot be normalized. If this number is used during the computation, the result may also be 0. Instead of checking for zeros during the normalization process, we check for zeros at the beginning and terminate the process if necessary. The alignment of the mantissa must be carried out prior to their operation. After the mantissa are added or subtracted, the result may be unnormalized. The normalization procedure ensures that the result is normalized prior to its transfer to memory. The flowchart for adding or subtracting two floating point binary numbers is shown in the below figure. We have to take accumulator and BR. So this accumulator is equal to the 0 when we are transferring that value. So addition or subtraction, during the addition or subtraction, the two floating point operands are in AC and BR. The sum or difference is formed in the accumulator. Addition and subtraction, during the addition of subtraction, the two floating point operations or operands are in AC and BR. The sum or difference is formed in the AC. The algorithm can be divided into four consecutive parts. First one, check for zeros, align the mantissa, add or subtract the mantissa, normalize the result. A floating point numbers that is 0 cannot be normalized. In this number is used during the computation. The result may also be 0. Instead of checking for zeros during the normalization process, we check for zeros at the beginning and terminate the process if necessary. So we have to take one example to understand all the conditions. First one is a check for zeros, align the mantissa, add or subtract the mantissa, normalize the result. These are the four conditions are there. The alignment of the mantissa must be carried out prior to their operation. After the mantissas are added or subtracted, the result may be unnormalized. The normalized procedure ensures that the result is normalized prior to its transfer to the memory. The flowchart for adding or subtracting two floating point binary numbers is shown. The operation is termed with the value of accumulator being the result in accumulator equal to 0. And the arithmetic operations on floating point numbers consist of addition, subtraction, multiplication and division. So what we are taking the arithmetic operations, we have to form addition, subtraction, multiplication and division. So these arithmetic operations of addition, subtraction, multiplication, division, the operations are done with algorithms similar to those used on same magnitude integers because of the similarity of representation. Example, only add numbers of the same sign. Multiply operation, multiplicand in B, multiplier in Q. So I have to multiply the R1 into R2. So, or A into B. But here I am taking B into Q. B comma Q. So, B into Q. The resultant value here. Here B equal to multiplicand and it is a multiplier. Multiplicand and multiplier. So A tends to QS into BS, Q tends to QS into BS, 0 tends to A and E tends to 0. So A is the accumulator and SC tends to N minus 1. Here if condition equal to 1, it is go to the effective address EA equal to A plus B and shift right EAQ and SC tends to SC minus 1 to SC. So it is a flowchart of multiply operation with a multiplicand and multiplier. So when we are taking the arithmetic operation, example I am taking multiplication, I am going for the multiplicand with the multiplier. I will take one example to understand this one. So floating point multiplication, multiplicand and multiplier I am taking. So if anything, suppose maybe the multiplicand is 0 or maybe multiplier also be 0 maybe. So if BR is a multiplicand and QR is a multiplier. If BR equal to 0, what will happen? 0 into something, it will be 0. So maybe if it is 0, then the resultant value is 0, then it is directly go to the end. If it is not 0, then it is going to the next. If QR, that means multiplier is 0, maybe the result is also a 0 end. So if it is both are not 0, then it is multiplying. Multiplicand and the multiplier will be multiply. And if anything multiply will become, it will show and it will complete the task. Flowchart of divide operation. Dividing in AQ, division with B. So I am taking AQ and B. We are dividing two things. So it is a flowchart of divide operation. In the basic consideration of floating point arithmetic operation, I have to take the integer and floating point values with the Montesa and the exponent. So 537.25, we have to take the 0.537 into 25 into 10 cube. So these dot values shifted to here, 0.5372 into 10 cube. So it is a exponent and it is a Montesa. So m into r power e. The two ports representing a number obtained from multiplying m times a radix r and to the value of e. So the Montesa may be a fraction or an integer. We have to take the both options, fraction or integer. The location of the radix point and the value of radix r and assumed to be not included in the registers. So if I am taking the floating point addition and subtraction, during this we have to maintain 4 conditions. Check for zeros, align the Montesa, add or subtract the Montesa, normalize the results. So if I am taking 530, previously one example is there, 537.25. Okay. Next, align the Montesa. Is there a align Montesa? If aligning Montesa is there, not. 0.53725 into 10 cube. Montesa and exponent. So align the Montesa and or subtract the Montesa, normalize the result. Suppose I have to multiply 537.25 into 10 cube with 260.12 into 10 square. These are normalized? No. Here 537, 3 digits after it is fraction value. Here after 2 digits only fraction value is there. Here 10 cube is there. It is a 10 square is there. So here the Montesa is not same. Okay, multiplier and multiplicand Montesa is not equal. Then we have to go for the normalized, means we have to convert to this 10 square convert in the 10 cube. Then only exponents will be normalized and Montesa should be normalized. So align the Montesa and subtract the Montesa. Then only you have to go for the subtracting or addition of the Montesa. Then we have to go for the normalize the result. So the result also in the form of 10 cube only. And a floating point number that is 0 cannot be normalized. In this number is used during the computation. The result may also be 0. Instead of checking for zeros during the normalization process, we check for zeros at the beginning and terminate the process if necessary. The alignment of the Montesa must be carried out prior to their operation. After the Montesa are added or subtracted, the result may be unnormalized. The normalized procedure ensures that the result is normalized prior to its transfer to memory. So the flowchart of addition and subtraction of two floating point binary numbers is given. So we have to check these conditions, and the floating point number is 0 cannot be normalized. If the number is used during the computation, the result may also be 0. And instead of checking for zeros during the normalization process, we check zeros at the beginning and terminate the processes if necessary. So what are the normalized values are there? So we have to check all those things. Then only we have to go for. The alignment of the Montesa must be carried out prior to their operation. After the Montesa are added or subtracted, the resultant may be unnormalized. The normalization procedure ensures that the result is normalized prior to its transfer to the memory. And the flowchart for adding, subtracting two floating point binary numbers are shown. Here it is operation terminated with the value of AC being the result and the AC equal to 0 when we transfer. Here it is a addition, subtraction, multiplication, division arithmetic operation. We are taking one flowchart of multiplication operation. It is a divide operation. So in the computer arithmetic, we have to know what are the addition and subtraction, how we are adding and subtracting in the computer arithmetic. So computer arithmetic means not only addition and subtraction, multiplication, division also will be there, but here we have to study addition and subtraction on there. So in the addition, normally we have to add, but in the subtraction we have to go for the ones complement and twos complement. Before going to this one, we have to know sign to magnitude form. Is it plus value or minus value? Okay, if plus value means it is 0, if minus means it is showing as a 1, 0 means it is a positive value, if 1 is indication means it is a negative value. Okay, so in the addition, 0 plus 0 equal to 0, 0 plus 1 equal to 1, 1 plus 0 equal to 1, 1 plus 1 equal to 1 is a carry and 0 is a result. So here we are going for the addition, subtraction, multiplication and division. First one, fixed point binary data in signed magnitude, fixed point binary data in signed twos complement representation. So example I am taking, apply ones complement for the following: 1 0 1 0 1 1 1 0. Okay, so ones complement means in place of 1 we have to take 0, in place of 0 1, 0 0 plus 1, in the 1 plus 0, place of 1 0 1 0 1. So it is the ones complement result. Okay, so what we got here, 0 1 0 1 0 0 1. Okay, is it ones complement? Yes. So if I are adding one more 1 to the LSB, 1 plus 1 0 and 1 is a carry, 0 plus 1 1, 0 0 1 0 1 0. It is called twos complement. Okay, so ones complement means we are complementing. That means I am applying the NOT gate. A, if I am giving A, I am getting the A bar. 0 is 1. So like this, if I am giving 1 input, output will be 0. 0 input, 1 output, like this. Okay, it is called the ones complement. So we are complementing the value, that is a ones. After completion of ones complement, we are adding 1 to the LSB, that is a twos complement. Mostly ones and twos are using in subtraction. And in the floating point operations, the computers used for the signed magnitude representation for the Montesa. Here, addition and subtraction with signed magnitude data. Okay, suppose I am adding A plus B. But what is the condition? Is it A less than B or A greater than B or A equal to B? Suppose, sorry, not A equal to B, A minus B. So I am subtracting A with B. Here, A is the largest value or A is the smallest value compared to B. Is it any difference are there? Is it A less than B or A greater than B or A equal to B? If A equal to B means I will get the 0. If A is greater than means positive value. A less than value is means I will get the negative value. So depends on your subtractor value, the result will be positive or negative or 0 will become. So addition algorithm, how we are preparing the addition or subtraction algorithm. First is it A less than B or A greater than B? Then only I will be find out, I will get the positive value or negative value. 1 0 1 0 plus 0 0 1 0 addition. So 1 0 1 0 0 0 1 0, 0 plus 0 0, 1 plus 1 10, 0 plus 0 plus 1 1 plus 0. It is the result of resultant of addition. So it is a subtraction value. It is a greater than B. But I have to go 1 0 1 0 minus 1 1 0 0. Here A less than B. So for these conditions, what I have to do? We are going for the ones complement for this one. So 1 0 1 0 subtractor 1 1 0 0 subtrahend. So apply ones complement for subtrahend. So what will happen now? Apply the ones complement subtrahend. Here already 1 0 1 0 I know. So we are applying ones complement this one 0 0 1 1. I will add both 0 plus 1 1 1 plus 1 like this. Okay. So after addition of this one, I am adding this one. So it is the addition. So totally I'm finally I subtracted, but for what is the answer I will get means first ones complement subtrahend. After getting the subtrahend value, I'm adding. That is the a minus b. It is a condition operation. Plus a plus of plus b. Is it addition? Yes. Plus of plus ab. Plus a plus of minus b. Is it subtraction? Yes. Subtraction. A minus b. Okay. Is it satisfying a greater than b? Yes. Here minus of b minus a. So there are different conditions are there for comparison. Minus a plus of minus b. That means minus of a plus b. Here plus a minus b. Plus a minus b. Here minus b plus a. Which one is a less than b is satisfied. Here plus a minus b. Plus a minus b. Plus of b minus a. That means a less than b satisfied. Here minus a plus b. A greater than b. So there are different conditions are satisfied for this one. And it is the hardware implementation of signed magnitude addition and subtraction. It is a subtraction operation. But after when we came to here, we are going to hit this one. Why? Because here I am going for the a minus b means ones complement I am doing here. Then the resultant after the ones complement I am adding a plus b. So the resultant value I am getting like this. So it is going to after so first subtraction after the ones complement both are adding. It is the addition and subtraction of signed to twos complement. After the completion of first ones complement, we are adding one more to that ones complement. That is the twos complement. It is about the hardware implementation and hardware algorithm. Okay, these are the references. So we have discussed today computer arithmetic, addition and subtraction, and floating point arithmetic operations. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.